Okay, so yeah, I'm Simon. I come from a technology consultancy, FuturePrint Technology. We do a lot of work in a lot of industries, but including a lot of work in inkjet and digital deposition. I should stress when we start, we have a number of experts in inkjet and digital deposition. We also have a number of experts in machine learning and AI. I'm actually neither of those things. I'm quite a generalist. I look at where we can apply technologies. So that's my main interest. So first of all, we've spoken a little bit about this, but the term AI encompasses quite a raft of different technologies. And I think it's important to reflect that there's a broad spectrum of complexity, even among what is actually in some way intelligence within machine learning. There's also a lot of things within the hype at the moment that are actually just automation by computer that are called AI, which I'm going to leave kind of out of scope. But we have some very simple machine learning algorithms on one end of the spectrum, right through to some very, very complex AI systems. So just to give you a feel for what I mean by a machine learning algorithm, I'd like you to sort of consider for a moment you're trying to train a computer to do a job. And so you take a load of samples, and all you want the computer to do is identify what the next sample is. So you come up with a load of training samples, which you map in a multi-dimensional space. So for every type of sensor you have, you've got a dimension in this hypercube or whatever it is. And you position all of these points, and they're all of the different training samples. And then you take a new sample, and all you do is you go, what are the k, so pick a number for k, say 10. So what are the 10 nearest neighbors to my training sample in this multi-dimensional space? And then you take a vote from these samples. Now that vote can be a simple vote, it can be weighted by distance, but at the end of the day, that's the concept of k nearest neighbors. So I hope you'll appreciate that this is actually quite a simple machine learning algorithm. It's very understandable, it's very reviewable. You can give some data and you can know what you're going to get back, and it's repeatable. It will give you the same result every time. If you give it the same input, it'll give you the same output. I'd now like you to think about systems such as deep neural networks, transformer models, and adversarial networks. Now, a lot of these fall into the black box territory. We call them that because they're unintelligible. They often comprise potentially billions of parameters, far beyond what we can understand as humans. And also, they look at really weird things that just don't quite make sense and are very difficult for us to tease apart. They can also include an interplay of multiple black box systems. And I think a key thing to take away here is these can be unrepeatable and potentially chaotic, especially when it comes to generative AI, where some of the big breakthroughs have been introducing chaos with addition of noise. So if you go on to Leonardo AI, now Leonardo AI is an excellent image generating app, and it's free. You go on there and you ask it, this is using their real time, so this will literally, as you're typing, come up with images. You ask it for a hot dog. And you go, okay, that's great. That's a really good hot dog. So, is the product ready? Well, maybe, but let's just try it again. Okay, maybe the person applying the mustard was a bit distracted for this hot dog, but I think, while salad and weird mustard placement aside, I think you'd sort of still agree that that is broadly still a hot dog. Try it a few more times. It starts getting weirder, and possibly even macabre. So in a world used to precision and predictability, especially with computer systems, AI can throw up a few surprises. So AI is not a magic bullet, but that doesn't mean it's not useful. An AI deployed well can do a reasonable job of tackling many challenges, but often actually it can still be outperformed by traditional algorithms with a similar level of effort applied. So if you're trying to do something and you know what you're trying to do, quite often actually algorithms are better than AI at performing that task. So there are poorly suited challenges, but there are also challenges where AI performs exceptionally well. So what kind of challenge is AI suited for? So a good challenge for AI is likely to be too complex to make comparable algorithms with a traditional approach. And that can either be complexity from a number of different parameters that are coming in and adding complexity, or it can just be unanticipated changes, so you're trying to account for things you haven't yet seen. No one right answer. So generally, if it's something where you can come up with a confidence of it's most likely this, or this is a good approach, not necessarily the best, but it's a pretty good approach. That's where AI really shines. It won't come up with the optimized, perfect approach, but its good approach might be better than you can compute in a sensible amount of time. Situations where you've got lots of training data, and it's really important this training data is actually representative as well. So there's a famous, I'm not sure if it's apocryphal or if it's real, case of people training an algorithm to look between dogs and wolves. And all the training data for wolves had a snowy background. And it was very good at detecting whether there was a snowy background, and anything standing in front of that was a wolf. Not very useful at actually doing the task it was intended for. So quality is also important in the training data. And good ground truth to that data is also very useful. Now where this kind of goes into a gray area, but you do definitely need to have things grounded with some reality in order for the AI to be able to effectively train. Okay, so now I'm just going to pick a few different topics to talk about. And this really is just looking into a crystal ball. It's quite arbitrary. And as I say, I'm kind of peripheral to the industry. I'm not actually in it as you guys are. But graphics creation, obviously with generative AI, adding bleed to the edges of graphics, creating non-repeating patterns. There's all sorts of opportunities for creating graphics that are relevant. Checking of graphics for kind of triaging and simplifying automated workflow for web tools. I think there's a huge opportunity. I think both of those topics were covered pretty well by Tom earlier. Quality control and defect detection, and eventually causal analysis. Waveform optimization, so actually how we're driving the inkjet heads themselves. And also part of the RIP, the raster image processor, half-toning process. So yeah, those top two I've seen discussed a fair bit, and they've already come up today, so I'm not going to talk about those. We'll jump straight on to the bottom three. So quality control and defect detection. Printed graphics will never be a perfect match for digital artwork. So you don't get exactly what's on the file. There will always be deviation. So what constitutes a defect is actually subjective. And it's also worth saying that textured image regions may be pretty tolerant to some of the things that may constitute defects in other parts of the image. Where some parts of the image, you just want it to be as smooth as possible. Other parts, you want to get that detail in. Color distance, LAB color distance is designed to mimic perception, but it's context, frequency, and lighting dependent. So banding can often actually be seen far below the discernible difference for level of color. And high-speed printing makes high-resolution inspection very data-intensive. So even RGB cameras are likely to generate unmanageable amounts of data at full resolution. Hyperspectral color inspection would add another level, but it's worth noting that the gamut of an RGB camera and its ability to discern colors is far below what the human eye can do, so it's going to be challenging for it to work with that alone. So this may mean that high-speed printing is only compatible with spatially undersampled vision systems. So given the benefit of digital printing is its flexibility, a QC vision system would need to identify defects on an uncontrolled varying graphics for real-time validation. And Simon's already touched a fair bit on this. So how good a fit is that for our points? So complexity. Given the infinite variety of graphics to detect on, the challenge is certainly complex enough to benefit from AI. There's no one right answer, so escalating defects, again, is something that you can say, hey, this looks like a defect, and someone can go, oh, actually, no, that's fine, or, yeah, that's an issue, let's stop things and sort that out. For training data, there's a huge amount of defects might be rare and difficult to recreate realistically. So there may be a challenge to overcome there. Ground truth, I think, is the key thing, where if there's enough value to introduce enough ground truth to train these models, then that's where this will come into its own. It may be the case that for the majority of defects, so missing jets, banding, and color difference, you might actually find that once you've taken all that data and understood what you're looking for, that algorithmic assessment might actually outperform AI. But AI might give you a very good first step to finding that. And also it's worth noting that during commissioning, where you're printing test cards and things, this sort of approach could also be another, it could be another good application. So moving on to waveform optimization. So the waveform drives drop size and velocity, as well as satellite generation and potential for other defects. Increasing waveform complexity is already unlocking benefits. So multiple pulses to acoustically excite to create larger droplets, that sort of thing. But at high speed, the ink dynamics from previous drops can influence jetting quality. Compensating or addressing this will be very difficult because it's a very complex interaction of parameters from unknown previous history of what's just been printed. AI may be very well suited to learn the impact of the driving patterns and formulate compensated waveforms. This might enable higher velocities, so increasing throw, placement precision, tolerance to turbulence, that sort of thing. Could also unlock larger drop sizes, giving more drop sizes for multi-level screens, and also higher driving frequencies for faster printing. So on our set, actually, we've got a really good hit for all four of our sort of qualifiers for whether it's a good fit for AI. So it's clearly very complex. A waveform that's satisfactory is, you can probably improve on a cookie cutter waveform and actually make something that's better tailored. There's lots of training data available. Camera data for print quality and also droplet formation could be really easy to create. And it's readily measurable automatically. So onto half-toning. So you probably all know what half-toning is, but I think the key thing to focus on here is, in some parts of the image, the half-toning is trying to just make things as smooth as possible. You want a gradient, you don't want contours, you want it to just look nice and smooth. Other times, you want perceived detail and resolution. You want to be able to create those high-frequency features and get them exactly as you want them. And in some areas, you specifically want clarity around certain features. So if you've got small text, that's very important. There's a whole suite of complex challenges. I'm not going to talk through all of them, but there's a suite of complex challenges here that all come together to make this a very difficult thing. There's a reason why there are very, there's very specialist software for RIP, and it's a very challenging problem to solve. And there's lots of different things competing there. But one of the key things here is minimizing computation time will be critical for any applications here, because you need to keep up with the press. So, I think traditional RIP software does a good job, but I think there's room for improvement that's inaccessible due to the complexity at the moment and due to that computational challenge. But AI's ability to fuse these different requirements into a single action could be useful. I think being able to create a custom-generated dither screen that's better suited for particular image or graphic types, but also that avoids voids and clusters locally where you're looking at so identifying what you're trying to do with different parts of the image without having to manually say, this is text, I really want this to come through clearly, and this is smooth, and I really want it to not do, is something that AI could be very powerful at. And doing this very well, especially for lower resolution applications, such as ValveJet and other things where droplet size is larger, you might find that the optimization of perceived print quality can dominate over the computational simplicity. So I think here, on our tests, it hits most of the tests. I think in order to get a ground truth, you probably would need to manually train an adversarial AI. So this is actually an AI that marks the homework of the AI we're creating and says, this is something that will look smooth where it's supposed to look smooth. This is something that you can read that text successfully. I think the key thing is real-time computation, simplifying that will be absolutely critical here. AI is traditionally very computationally intensive, but it actually has quite some promising applications for edge processing. So effectively, you put all the computational complexity in creating the AI model, and then you create a relatively simple deployment of that. And the key thing is this needs to be simple in runtime. Looking further ahead, Developments in hardware and computational efficiency might then enable some combinations of this. So real-time optimization of the waveform per nozzle, closed loop with printed output imaging. Actually, it sounds from what Simon was saying a few minutes back that actually some of this might actually be closer than perhaps I thought. Dither map and waveform generation in consideration of pulse train to enable increased speed. There's potential to sort of roll those together, and then real-time defect detection, causal analysis, and compensation in dither and waveform, picking up again. Finally, targeting computational effort localized on where that is really critical to drive the image quality. I think there are areas where you could probably get away with reducing the computational effort applied, and then areas where it really drives image quality. And so those optimizations may also be very valuable. So closing thoughts. Beyond the hype, AI does have promise for helping smarter driving of inkjet heads. Capturing data now may enable easier future AI deployment. So as AI evolves, its capabilities will increase, but its hunger for data will be always there. Capturing the right data relating to the physics of the printing process is going to be important. Capturing any old data might give you some inputs. AI is very good at divining from tea leaves and seeing from very low quality data, but the higher quality that data is, the better. And then once you've captured that data, you might actually find that in itself unlocks insights. So it may actually be unnecessary right now to deploy the AI to fix things once you've got the right data and you're looking at it in the right way. And traditional algorithms actually may be beneficial in the short term, while also future-proofing to be ready for that AI going forward. And that's everything from me.